Exploring Life. Chapter 10, Energy. Part 1. Today, we're exploring Earth's energy balance, where our planet's energy comes from, how living organisms use it, and how it's stored and preserved, both within organisms and across ecosystems. But first, the basics. Energy is the ability to do work, to cause change or make things happen. In science, work means moving an object against a resisting force, like pushing a box across the floor against friction, or transporting a chemical across a membrane against its concentration gradient. Understanding the different types of energy is essential to understanding how both life and our planet function. Kinetic energy is the energy of motion. Anytime something moves, like a rolling ball or a speeding car, it has kinetic energy. Light energy is a form of kinetic energy too. It comes from fast-moving particles of light called photons. This is the energy that travels from the sun to Earth, powering photosynthesis. Thermal energy is another form of kinetic energy. It comes from the movement of atoms and molecules. The faster the particles move, the higher the temperature. Potential energy is stored energy based on an object's position or condition. Think of an icicle hanging from the edge of a roof. It's not moving yet, but it has the potential to fall and release energy. Chemical energy is a type of potential energy stored in the bonds of molecules. It's the energy locked inside food, fuel, and even your own cells, ready to be released during chemical reactions that keep life going. Energy is measured in joules, abbreviated as J, the standard unit in the metric system. But you're probably more familiar with calories, watts, and degrees, especially when it comes to food, weather, and household appliances. For reference, 1 calorie is roughly equal to 4 joules. 1 watt equals 1 joule per second. 1 degree Celsius increase in 1 gram of water is also about 4 joules. Using standard units allows scientists to make consistent comparisons across different systems and forms of energy, from the energy that moves a transport vesicle within a cell, to the heat in your coffee, to the energy powering a thunderstorm. Thermodynamics is the branch of physics that explores how energy is transferred, transformed, and conserved. Here are a few everyday examples of energy transformation. Kinetic energy can turn into heat. That's why we shiver when we're cold. Muscle movements create friction and generate warmth. Try rubbing your hands together, you'll feel it. Chemical potential energy can be transformed into electrical energy. For example, ATP powers cellular pumps, moving ions across membranes and creating charge differences. These and other energy transformations happen constantly, from the microscopic reactions in your cells to the large-scale processes that shape Earth's climate. 2 fundamental laws of thermodynamics shape how energy flows and transforms, everywhere from deep space to your own body. The first law of thermodynamics, also called the law of energy conservation, lays down a powerful truth. In a closed system, like the universe, energy can't be created or destroyed. It can only change forms. So, where does your energy come from? When you eat, your body doesn't create energy, it simply transforms the chemical energy in food into kinetic energy that lets you move, breathe, and live. In other words, energy is always on the move. It just changes costume. The second law of thermodynamics deals with a concept called entropy, which is a measure of disorder or randomness in a system. According to this law, Every energy transformation increases the overall entropy of the universe. In other words, energy tends to spread out and become more disorganized over time. As energy disperses, it becomes less useful for doing work, leading to greater chaos in the system. This is why no energy transfer is 100% efficient. Some energy is always lost as heat, increasing entropy. We'll use a money analogy to better understand thermodynamics. Think of the first law of thermodynamics like having a set budget. You can spend it immediately, move it around, or change how it's used, but it's still the same amount. Not more, not less. That's energy conservation. The total amount stays the same. Now it's your turn. Propose your own analogy for the laws of thermodynamics. How would you explain the first and second laws using something familiar, like money, food, traffic, or even a game? We've explored the types of energy, how it transforms, and the laws that govern its flow, from cells to the universe. In part 2 of the lecture, we'll go further. Where does life get its energy, and how is it stored, shared, and recycled across organisms and ecosystems? Follow the prompt and see how much you recall from the topics we've covered. Don't worry if you don't remember everything, review the materials as needed, and use this as a chance to learn even more in the process.